Hello friends, today's question: a metal rod of length L and mass m is pivoted at one end. A thin disc of mass m, capital M, and radius r, which is less than L, is attached at its center to the free end of the rod. Consider two ways the disc is attached. Case A, the disc is not free to rotate about its center. Case B, the disc is free to rotate about its center. The rod disc system performs SHM in a vertical plane after being released from the same displacement position. Which of the following statement is or are true? So these are the four statements, and the both statements are a combination of restoring torque as well as angular frequency. So this is the mean position of the rod, and this is you can say displaced position, and we have disc. So in the two cases, first case disc is not free to rotate, and in second case this disc is free to rotate about this, you can say this joint, which is at point where it is connected to the rod. And we have to find out what will be the relationship between the restoring torque in case A and case B, as well as angular frequency in case A and case B. Okay. So in this case, we are going to start with the moment of inertia. In the case A, we are going to find moment of inertia. In the case B also, we are going to find moment of inertia. And then we are going to, because the angular frequency is related to moment of inertia, and torque you can say drive independently, that's not dependent for the moment of inertia for this particular question. So we are going to start with the, you can say, moment of inertia. In the first case it is said that disc is not free to rotate. It means this disc is free, and in that case we are going to treat this disc as a point mass, and we are going to find out its moment of inertia with respect to this pivot point. And we are also going to find a moment of inertia for the rod about this pivot point. That is, the total moment of inertia will be equal to this plus this. In the second case, we are also going to do that, but in the second case, we have to remember that this disc is free to rotate. Okay, that's the only difference, major difference rather, between the two cases. So let us start with case A. And case A states that the disc is fixed to the rod, that is, it cannot rotate about its center. It cannot rotate about its center, and center, let us call this a center as C. Okay. So therefore we can say that we have to include the disc moment of inertia about the pivot point. So we can say from here, so we have to include disc moment of inertia about the pivot point, and let us call this pivot point as P. Of disc moment of inertia about pivot point P. Now the moment of inertia, let us start for the rod first of all. So you can say moment of inertia of the rod will be equal to, let us call that I rod, and that will be equal to 1 by 3, and its mass is given as small m and length is so L square. So this is the pivot point, and the moment of inertia is at the end of the rod. So we get 1 by 3 ml square. Now the moment of inertia of the disc about the pivot point, it is going to have two components. first component will be of the disk about its own center, and then we have to use the, you can say, theorem of parallel axis to find out its moment of inertia about this pivot point. You can say moment of inertia of disk about the pivot point P has two components. First is its own moment of inertia across its center. Its own moment of inertia about its center, which we have taken as C. And let us call that moment of inertia of the disk about center. And that will be equal to half m and r square. M is the mass and r is the radius. Now the second part is disk moment of inertia about the pivot point. Disk moment of inertia about the pivot point, which is taken as P, pivot point, and pivot point is at L distance. So in order to solve this, we are going to use theorem of parallel axis. Using theorem of parallel axis, and from the theorem of parallel axis we can say its moment of inertia, that is I, of the disk about the pivot point will be equal to moment of inertia of the disk about its center plus mass and the distance between the center and the pivot point, that is ml square. So we substitute the value, we get I disk pivot will be equal to half m r square plus ml square. So therefore the total moment of inertia in case A, thus total moment of inertia for case A, let us call that IA, and that will be equal to moment of inertia of the rod plus moment of inertia of the disk about pivot point. So we get IA will be equal to 1/3 ml square plus half mr square and plus ml square. Let us call this equation 1. Now similarly, we are going to discuss case number B. Case B. Yeah. So in case B, it's said that the disk is free to rotate about its, disk is free to rotate. Disk is free to rotate around its center, and center we have taken as C. Therefore we are going to treat it as a point mass connected at the end of the rod. Therefore we treat it as a point mass connected at the end of the rod, and we are going to treat it as a point mass connected to the end of the rod for calculating the system total moment of inertia, calculating the total moment of inertia, and which we are going to call as IB, around the pivot point. So for the second case, we can just draw a rough diagram also. So this is our rod, and the disc will be now treated as a point mass. This will be the disc, and the disc is going to have mass m, and the length of the rod is given as L, and the mass of the rod is given as small m. So therefore we can say that this IB, moment of inertia of the entire system, will be equal to moment of inertia of the rod plus moment of inertia of this point mass, that is disc as a point mass. You can say moment of inertia of rod plus moment of inertia of disc as a point mass. And moment of inertia of the rod will be equal to 1 by 3 ml square. Moment of inertia of the rod will be equal to 1 by 3 ml square, and let us call that as I rod prime. So in order to differentiate from the first case, I prime rod will be equal to 1 by 3 ml square, and similarly you can say moment of inertia of the disc about the pivot point. Okay. And please keep in mind, this is about pivot point, P, and this is pivot point P. And for the second case, we can say that moment of inertia of disc a point mass m, small m, at a distance L from the pivot point, that is P. So now this is the point mass, okay, and this is for disc, and this disc is at a distance L from the pivot point. So therefore we can write I prime disc about the pivot point will be equal to ml square. Therefore we can write that the total moment of inertia IB for case 2 will be equal to 1 by 3 ml square plus ml square. So we have two equations. First equation was for case A, and second equation for case B. And if you make a comparison between equation 1 and 2, you can say from equation 1 and 2, you can clearly see that moment of inertia of case A will be equal to moment of inertia will be greater than moment of inertia for case B. It is very clear from the equation itself. Okay, if we add them, this will be equal. Sorry, 1 second. This is small m, not capital M. ml square, and this will be small m. My mistake. So from the equation itself, it is clear that this quantity is on the higher side as compared to equation 2. Now let us find out what will be the restoring torque as asked in the question, because in the question we are interested in only the restoring torque and angular frequency. So first we restoring torque. So we consider a small angle theta to which it is being displaced. So this is theta angle, and we have considered this a small angle. We say for small angle theta, the restoring torque is given by the gravitational force that will be acting on the center of mass. By the gravitational force acting on the center of mass of rod plus disk system. So the restoring torque is not dependent whether the disk is rotating or not rotating. It is only dependent upon the gravitational force acting on the center of mass. Okay. So it means as the length of the rod is fixed, the radius of the disk is also fixed, or we can say mass of the disk is also fixed, as well as the mass of the rod is fixed along with the length and radius. Therefore, the center of mass is not going to change in case A as well in case B. It is going to remain same. So from here we can say, since center of mass does not change for case A and case B, therefore we can say that the restoring torque for case A will be equal to restoring torque for case B. So both the torque will be, restoring torque will be equal, and you can just write the value will be, this will be equal to minus, and we have here ml by 2 plus ml and g theta. Normally it will be sine of theta. We had taken theta to be small, so we can write g of theta. Okay. So it will be, it means same for both. Restoring torque will be same. So the option that are available to us is restoring torque case A will be equal restoring torque in case B. So option number A is correct. So this is our true option. So option A is true. Is true. Now let's go to the, you can say, the angular frequency. We know that angular frequency, the formula, angular frequency, if it is at omega, is equal to, we have restoring torque divided by moment of inertia. So we can write this same formula for case A as well as case B. So we can say for case A, we have omega A will be equal to restoring torque, let us suppose, is given as tau A, and moment of inertia we know is given as IA. And for case B, let me write it here. This is our tau A and this is our tau B. And for case B, omega B will be equal to square root of tau B, and we have IB. But just we proved that tau A is equal to tau B, and we also proved that moment of inertia of A is greater than moment of inertia of B, and there is an inverse relationship between the angular frequency and moment of inertia. From here we can say that omega A is inversely proportional to IA, and from here we can say that omega B is inversely proportional to IB. So we substitute the values for the sake of calculation. We can write IA will be equal to 1 upon omega A is greater than 1 upon omega B, and this tells us omega B is greater than omega A. It means angular frequency of B is greater than angular frequency of A. This tells us angular frequency of B is greater than angular frequency of A. So we check options that are available to us. We can say that angular frequency of B is greater than angular frequency of A. Okay. So option number D is the correct option. It is written just in reverse order as compared to this. So you can say option D is correct. So this completes the question. Thank you.